guys, this is the third lesson in year 9, and we're continuing our lesson on the atom. Now we're going to talk about trends in the periodic table. Now, why are trends important? Trends are important because it allows us to determine the chemical properties as well as the physical properties of elements in the periodic table as arranged in groups. So this lesson will focus on some of the elements in 3 particular groups. Group 1, alkaline metals. Group 7, the halogens. And group 8, the noble gases. Alright, so let's first talk about the alkaline metals. Alkaline metals are everything in the group 1. It is the far left side of the periodic table. Okay? It starts with lithium, sodium, and then potassium, and it goes on and on and on down there. But we're not going to talk about the other 2 that's beneath that, or 3. We're just going to focus on this first 3 here. Lithium is the top of the group 1 alkaline metals. Now, the Bohr model is depicted here, in which it has 3 protons, 4 neutrons, and 3 electrons orbiting around it, 2 in the first shell, and then the last one in the outermost second shell. And scientists also use what we call electron structure. Let me write that down right here. Electron structure. To describe the structure of the electrons surrounding the nucleus. So 2, 1 indicates that there are 2 electrons on the first shell and 1 electron on the outer shell, the second shell. And it's drawn like that. Now, why are we focused on the electron structure? Electrons are what defines chemistry. It allows us, if we understand what is going on in the electrons, we can predict a whole slew of reactions and what is going to happen. And this is exactly what I want you to do later on, to search YouTube videos on how alkaline metals react with water. Alright? But for now, let us go on to sodium. Sodium is beneath lithium in the periodic table. Now, its electron structure is 281. What does that mean? Again, 2 electrons on the first shell, 8 electrons on the second shell. We can count that. 1, 2, 3, 4, 5, 6, 7, 8. Now, why do we write the 2 electrons in pairs as so? This will be important when you go to learn higher levels of chemistry, in that electrons like to pair up with each other. It's like finds its partner. It also has to do with the electron cloud model we were talking about, where electrons will spin in certain directions in its orbit, but that's just higher level chemistry. But just to know that this is how we draw electron pairs in the Bohr model. And we have 1 electron here on the outermost shell. But as we move down the alkali group, we can see the next one is potassium. Potassium has the electron structure of 2881. It means it has 4 shells in total. 2, 1 shell, second shell, third shell, fourth shell. Okay? It has 2 electrons in the first shell, 8 electrons in the second shell, 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons on the third shell, 1, 2, 3, 4, 5, 6, 7, 8. And then 1 electron on the outermost shell. Now, if you look at the electron structure of the alkaline metals, you will notice it has 1 similar number. 1, 1, and 1. This tells us that that lone pair, that lone electron in the outer shell is way out there by itself. All right? And this is important because this electron, being so lonely, wants to find a better home. But all the other homes in the other shells are completely filled up. They're fully occupied. You can't force any more electrons down in there. All right? So that electron is willing to move or migrate to other elements. And this is exactly what's going to happen. So pause the video right here, open a new YouTube tab, and search for lithium in water, sodium in water, potassium in water. You may say other alkaline metals in water, but all I want you to do is focus on the reactivity of lithium, sodium, and potassium in water. All right. So, what did you see? You saw that potassium, when reacted with water, is a lot more reactive than the lithium when it reacted with water. Am I right? Why is that? That's because if you look at the Bohr model, you would see that this lone electron on the outer shell is very far away from the nucleus compared to this electron on the lithium atom to the nucleus. Because it's so far away, there is relatively little electrostatic interaction. Let me write that down. Electrostatic, like static electricity, electrostatic interaction between this lone electron to the nucleus. There are a variety of reasons why this is so, but we're not going to get down to that. This means that this is so much more willing to go away, leave the potassium atom to, in our example, water. It's going to leave and form hydroxide with water, okay? And don't worry about hydroxide, we'll talk about it. So that is the trend of group 1 alkaline metals. Alright, let's move on. Group 7. Group 7 are called the halogens. They're basically 3 that you kind of need to know: fluorine, chlorine, bromine. There are other more down there, but let's not worry about that. Fluorine and chlorine are gases at room temperature. So that means they combine together to form diatomic models. Diatomic means 2 atoms in 1 molecule. So fluorine is going to form diatomic gases in the atmosphere. So with chlorine. But that's not the important thing because we're talking about trends. Now, if you look at the electron structure of fluorine, you'll see it's 2,7. And if you look at chlorine, it's 2,8,7. Now, the 7 here are the common trends in halogens in terms of its electron structure. This means that halogens are very receptive to accept electrons from other atoms, either from group 1, group 2, whatever, or the transition metals. It's willing to accept atoms or share atoms with itself or other means, okay, other atoms. So this is exactly what is going to happen. And scientists have made observations that it is true. This group 7 of halogens are very electronegative, which means that they are very receptive of electrons. That means they want to attract electrons to it. Why? This is because it wants to achieve a full octet shell. Octet meaning 8. Okay? If you count the electrons on the outer shell, you see 1, 2, 3, 4, 5, 6, 7. 7. That means it wants to accept one more electron. When it accepts one more electron, it is happy and full. Like, after a buffet. So, that is the trend of group 7 halogens. Finally, we'll talk about group 8, the noble gases. These are the aristocrats of the periodic table. Aristocrats meaning they're rich, they're wealthy, maybe a little snooty. These noble gases are basically unreactive, or as we call them in the chemistry world, inert. Inert means unreactive. Here we go. I-N-E-R-T. So, basically we're going to just talk about 3 of them. Helium, neon, and argon. Helium has a full shell at 2. Now why just 2 and not 8? That's just the law of nature. The spatial constraint that the first shell can hold. Only 2 electrons. Alright? And as you grow bigger, you add more electrons and protons and neutrons. The other noble gases is neon. Now it can hold 8 electrons in its second shell. Argon has 3 shells, and it will also have 3 full shells. 2 on the first shell, 8 on the second shell, and 8 more on the final shell. In general, noble gases don't really react with anything else. Alright? So that's all we have to talk today about the trends in the periodic table.